This meeting is being recorded.
For problem 8 from chapter 15, we are asked to predict the chemical shifts for each of the signals that we expect to find in these compounds shown below. So I've blown up the structures for compounds A and B, and we can work through these together. And then you can follow a similar technique for compounds C through E. So let's take a look at compound A here. And we'll begin with these methyl protons shown here. And we know that to calculate shift, we start with a 0.9 ppm for methyl protons. Now we see that these are not alpha to a carbonyl, but they are beta to a carbonyl right here. So we know that about 1/5 of the signal would be seen. So we're going to add, instead of 1.0 for a carbonyl, we'll add 0.2 ppm here. And we would expect to see this signal around 1.1 ppm for those three methyl protons. Next, let's move to the protons that are on this alpha carbon here next to the carbonyl. So we know that these are now methylene protons instead of methyl. So there's the two here. So we start at 1.2 ppm for methylene protons. Then we know that this is, again, alpha to that carbonyl. So we're going to add 1.0, and we expect to see a signal around 2.2 ppm for these protons here. Now let's move over here to these two methylene protons. So once again, we'll begin with 1.2 ppm because they're methylene protons. They are alpha to an oxygen of this ester here, right? So we see alpha to that oxygen. So we're going to add 3.0, and we should expect to see a signal around 4.2 ppm for these two protons. Then we have two more methylene protons shown here. So once again, we will start at 1.2 ppm, and then these are now beta to that oxygen. So instead of 3.0, we divide that to be about 1/5 of the signal, so we add 0.6. So we should see these protons giving a signal around 1.8. Then we have last here are three methyl protons. So they begin at 0.9 ppm, and we're going to add nothing to those. So for these three protons, we would expect to see that signal at about 0.9 ppm. So again, we have 1, 2, 3, 4, 5 distinct signals that we should see. Let's take a look at our next compound here. And we should have three distinct signals now. So let's begin up here. So we have our two methylene protons. So we'll start them at 1.2 ppm. They are alpha to this oxygen here, right? So that's alpha to that oxygen. So we're going to add a 2.5 ppm. And then they are alpha to a carbonyl. So we're going to add 1.0. And now we can add all these together, and we should expect to see this signal around 4.7 ppm. Remember, when you're alpha to an oxygen, it depends on if it's just an oxygen or an oxygen or an ester, etc. So that's why we added 2.5 instead of 3.0. Let's move to these protons down here. So we have two down here. And again, they are alpha to oxygen. So we start them at 1.2 because they're methylene protons. We add 2.5 being alpha to oxygen. And these guys are also beta to this oxygen here, right? So this would be the alpha, this would be the beta position to that oxygen. So we're going to add, that's the 1/5 of 3.0 because it's an oxygen of that ester. So we add all these together and we get about 4.3. And our last group, we're going to have 1, 2, 3, 4, 5, 6. So both of these methyl protons here, we would start these at 0.9 ppm. Then these are going to be beta to an oxygen. So we can add 0.6 ppm. And that would be from this oxygen up here. So that's why it's 1/5 of 3.0. So collectively, we would see a signal around 1.5 ppm. So again, compound A, we have 5 distinct signals. Compound B, we would see 3 distinct signals at these shift values.